Okay, and I'll share my screen and jump right in here. So, hello and welcome. What I'll ask people who are here in the auditorium is just to monitor the Slack channel for this tutorial in case folks who are on Zoom or someone in this room asks a Slack question. And if you're feeling so inclined, just shout at me. I'll just say also for folks who are on Zoom, feel free to unmute yourself and speak. You will be heard. There's a Zoom owl right in front of me, so I'll hear you talking if you just interrupt me, and feel free to do so. And same for people in the room, feel free to interrupt at any point. And ask questions. The goal here is to be pretty useful. I have a plan for what to do, but we don't need to necessarily go according to this plan. The way I think about this tutorial is a little bit taking stuff that you learned in the programming part and extending that to thinking about a little bit more about software engineering, and particularly about how to make code that is reusable. It's kind of, we sometimes talk about the hidden curriculum. This is, I feel like, part of the hidden curriculum of scientific computing is the fact that there are all these technical details about how code is organized, shared, distributed, that we don't talk about until you're sitting there trying to do it yourself and wading through documentation. So my goal is here to walk you through the process. And we'll take a simple example, really simple example as our basis for doing that. So imagine, and all of this material is, so I'm here in the Jupyter Hub, in the curriculum folder, there is a Rokem Python libs. And it's a series of markdown documents. It's going to be like notes about what I'm going to talk about. So I'll follow this roughly, but then deviate ever so often. So this is more of a kind of document you can read, and I'll use it also as my notes to make sure that I stay roughly on track. So I'll start by just first prefacing and saying that not every piece of code that you write needs to be shareable, usable by others. There's sort of a minimum of standard that we think about when we think about reproducible research, but that is more about your ability maybe to run the code that somebody else wrote with their data and get the same results. That's sort of one definition of reproducibility. And that code doesn't necessarily have to be something that can then be translated in order to run on your data. It runs on their data that they've provided together with their code. And it's a fairly, let's say, fairly high standard of reproducibility already. And we can talk more about what to do more in order to make it even more reproducible. There are always steps you can do to make things more reproducible. But sometimes you find yourself writing some code that is broadly useful. I find myself often starting a project with some data in a Jupyter notebook where I'm doing some analysis, and I find myself writing some code. I'll be importing some functionality from some library. I'll be writing some code. And then at some point while I'm doing this analysis, I'll realize, oh, this piece of code that I wrote right here, that should be a function. That should be a piece of, often this will be when I'm tempted to copy and paste that code into another cell. Instead of copying and pasting, the right way of copying and pasting code is to write a function and then reuse that function multiple times. So I'll sit there, I'll be doing data analysis on some data, and I'll write some functions. It's when I start another notebook and work on another data set and find myself tempted to copy and paste that function from one notebook to another that I realize that what I need actually is a module with functions, a library that contains functions that can be used broadly within, say, one project. My solution to this problem that is not broadly reusable is to have a little file called tools.py within my project. I have a directory, I'm tracking it with Git. We'll talk about Git later today. And I have my notebooks in there, and then I have a file with tools in there. It's when I find myself wanting to take some tools from this to another project that I'm now thinking, okay, this is where I need to create something that is a library of tools that can be used broadly across different projects. Maybe if it ends up being the case that somebody else asks me, hey, can I use your code that you used over there in my other, then that's when I start thinking, okay, this is actually something that needs to be packaged in a way that others can easily download and install into their machines. So that's the stages of what we'll see in this tutorial, what I just described. And this is something, just what I described to you now is something that happens to me all the time. I go through this, getting to like, I need a Python library that does all this, that others can download and install is a relatively rare occasion. But this, like, I want to copy and paste code from here to here is something that you're probably also familiar with. So let's start with the first step of that. So that's just to say, not all code needs to be shareable, reusable, follow all the standards here. But if you're going to create code that is, intended for others to use, maybe next week when you're hacking, you'll be interested in creating a library that does a particular thing. Maybe you want to practice doing these things. It's a good opportunity to try to put all these things into practice. So let's say that I'm in the course of my work on analysis of diffusion MRI data. I've written the following code in a script or in a Jupyter notebook. If it's in a script, it'll be in this file analysis.ipynb. That's the file format for notebooks, or maybe analysis.py if it's in a script. And this is the code. I'm importing some stuff. I'm importing NumPy and pandas. Maybe I read some data from some input data folder that I have in my project. And then I extract from this data frame that came to me here from the CSV file, some particular property, maybe the radius of the blob in there. And then I do some calculation and the area and circumference of this blob. Let's imagine this as a circular blob that can be characterized by area and circumference. And then I create a new data frame and immediately also save it out as output data into some new file called blob property. So maybe just to what's the problem with this code? What prevents this code from being reusable by others, reusable by me? Before looking at my notes. Yes, back there. So there's hard-coded file names and file paths in here. That's one thing. Yeah, so I've hard-coded some elements of this particular data set and analysis that make it so that I would have to change some of this code in order to run it elsewhere. What are some other things you see here that are making this hard to be reusable? Well, it's literally not reusable. It's locked inside of this script, right? I can't access it from if I'm trying to run something somewhere else. How would I get this code over there without copying and pasting? So that's one thing we'll solve soon. And then another element here that I think is important is just, and is important when thinking about software design is what we call separation of concerns. This code does not have separation of concerns. It mixes file input and output with data munging a little bit, sort of processing the data with numerical computations on the data. We're doing different kinds of computations here. Maybe this is not a very complicated computation, it can be, but we haven't separated the concerns that we have here sufficiently. So that's one thing we're going to think about next. So we're going to start with the separation of concerns. We're going to isolate different elements of the code. In this case, I'm doing a simple separation of concerns to take the elements of the numerical computation I'm doing and encode them in functions. So I have the data is the radii of, there's a column there with the radii of different blobs. And what I'm writing here are functions that calculate the area and calculate the circumference based on the radius of a particular blob or a series or an array of blobs. And then now I've relegated the input output down here. It's a little bigger. I've relegated the input output to down here. And in between, I do sort of the data munging computation. Now, this is still inside of this analysis script. This is a nicer analysis script, and this might be the next step that we do is we see, oh, there are some numerical computations here that we'd like to separate into functions. But the next step that we might do is actually move those functions out into a separate file. As I told you, every one of my project has a file called tools.py. Here we're going to call this file geometry.py. And in geometry.py, we will write these functions out. So here are two functions. They're nicely written. Written out, separating the two different computations that we can do. A few things about these functions. So this is the entire file, geometry.py, that we're using. I'll actually go and start this also, so we can do this in parallel. So I'll start a project here called geometry. And in geometry, I will create, so just a little bit of Jupyter stuff. This plus here takes me to this launcher, and I can launch a notebook here. This notebook won't quite work, but I can copy this code into it that I had here. And so this won't work because there is no input data here, but this could be, and I should rename the file. Maybe I do something that I'll do often, which is to name it something like 2023-08-08 analysis of blobs. Just a way for me to see when I did what. I'll end up with lots of these notebooks in some of my projects, and it's nice for me to see when I did what, so I can kind of follow along. So this is the kind of monolithic version of this. What I'm suggesting now is that we can add a Python file in here, call it, rename that geometry.py, and then take these functions that I've created here and copy them into this. Into this file. So this really is the entire geometry file right now. We'll go in and edit this a little bit more. One thing to note here is, in addition to just the functionality, even more lines of code here are devoted to documentation. This is called the doc string for this function. Those of you who were here just before with John, or will view the advanced Python video, will see that he mentioned triple quotes enclose doc strings. This is a triple quoted string is a multi-line string, and Python knows that that multi-line string appears immediately after the function definition, that is associated with that function, the object that is defined as the function, as its doc string. And various facilities in Python will use that doc string as documentation. For example, I'll show you in just a second here, that Jupyter knows how to show you this doc string when you ask about that particular function. This doc string follows a very particular standard. It's every character here is, no character here is accidental. The first line is a single line description, enclosed by a period because it's a sentence. Then come the parameters, the inputs to the function, named parameters with a line of dashes under it, and then all the parameters. The way we describe the parameters is we have the name of the parameter, space, colon, space. This is very important. I'll describe in just a second why all these things are important. The data type, and then on the second line, the description of this with a period in the end, because it's a sentence. And then the next kind of thing that could appear here if the function does return something is a set of returns. And there are other sections. And this all is very meticulously implemented based on the NumPy, and I need to find my fingers here, doc string standard. NumPy, the numerical computing in Python library, implements a nice style guide that describes exactly how we should, that's the style guide for Python code, but I'm looking for the doc string standard, which is in here, doc string standard. Right, that explains from here down, explains exactly what sections the doc string should have. And how those should be formatted. One of the reasons to do this so meticulously, including the space before and after the name of a parameter or return, is that there are libraries, software libraries, that will take these doc strings and process them into a variety of other documentation formats. So you can generate a PDF of the documentation of a library. You can generate a website that contains this. And if you follow this very meticulously, those will render in a way that's pleasing and consistent across a range of different tools. So if you follow the NumPy docstring standard, immediately you have access to all these tools that work with documentation to create pleasing documentation for you and for your users. So that's why this documentation is so meticulously formatted. Okay, now one thing. So now we've this code may be not as relevant to us anymore because we've put a lot of it into function. So I'll comment that out here, and I'll just point out one thing about Python. The Python import statement is when you're importing things from a library here, Python follows a sequence of order in order to figure out where it should be looking in your computer in order to find that thing. For example, NumPy is installed somewhere on this computer inside of the hub, inside of my sort of part of the hub, in a way that when I type import NumPy as NP, Python knows where to find that code, import into memory, and represent it as NP. The first thing that Python does when you ask to import, if you say import geometry as geo, for example, is that it looks in the present working directory. Wherever you're running this code as the present working directory, it will look for a file called geometry.py, and it will import that. It will run that code here and provide the names that are inside of geometry.py as accessible to you. So calculate area, for example, is a function implemented inside of this geometry module because that's how we implemented it. And it gets imported directly because the file is right there where we're running the code. And like I said, one of the useful things about these doc strings is that in Jupyter, if you type a question mark after the name of a function and execute that, it will put the doc string right there inside of your notebook. So writing nice documentation allows users of this code to then see the documentation. Okay, so this is already useful. We've taken some code that was locked inside of a notebook, and now we made it available within a directory to any code that we write in this directory, right? So this is the first kind of step in my process. Usually I'm analyzing some code, I see I have some functions, I move them into a file, and then I can import them directly to any notebook that is in the same directory. So that's already a good step. Let me pause here and see what questions do people have so far. I'll check on Slack also. Okay, let's see. Yes.
So that doctrine example that you gave, you said it's explicit and every character in every space is important valuable. Like PyCharm, you can do the auto quotation tab and it'll populate it, and it uses slightly different rules.
It's wrong.
So it's wrong.
So the question here is about PyCharm. Some IDEs will populate the docstring for you automatically, which is great. And I'm jokingly saying that it's wrong. It's just there are different ways, there are different standards that apply. In writing code, this code that I've written is very, very meticulously follows the overall standard for how to write Python code, which is PEP8. I think it briefly flashed here, but I'll show it again. This is the style guide for Python code, which is called PEP8. PEPs are Python enhancement proposals. And there are little documents that people write that say, how should the language be enhanced? And this was the 8th of them, or we're now in the hundreds already. I don't know if they follow a serial order, actually. But anyway, it's the one named 8. And it was written by Guido van Rossum and others. Guido was the person who started the language. This was written a little while ago and just describes how Python code should be formatted. And that's a very common, like if people don't write PEP8 code, that's frowned upon, and it's very widely followed, except by Google for some reason. You can find a Google code standard for Python, which deviates from this. So don't follow that one, please. But for doc strings, there's more standards. I'll still encourage you to use the NumPy one if you can, because of all the tools that follow from that for numerical, kind of within the ecosystem of numerical computing. Python is a great language because it's used so widely, but there are many different communities like web developers and other people, and numerical computing is like its own ecosystem. And if we follow all the rules together, then we can interoperate with other libraries and use tools together. Okay, what other questions do people have at this point? All right, so that was step one. I'll go back to let's go on to step two here. From module to package. Okay, so until now, we've seen how we take code and make it modular by implementing functions and being able to import it. Now what we'd like is something, let's imagine that we'll go to the next step where we'd like something that is more broadly useful, maybe across multiple projects that I'm working on. If there is no file called geometry.py in the present working directory, Python will fall back to the next thing. It will try to find a Python package called geometry. Now, what is a package? I've mentioned this word a few times here. A package is a folder in your computer that contains a file called __init__.py. And from now on, I will refer to this double underscore as dunder for short, because it's easier to say. So this is a dunder init file. If you have a folder and it has a dunder init file in it, that folder is now a package. In the simplest case, that file is empty and your package does nothing. And that's not very interesting. But in the slightly more interesting case, that folder with that dunder init file contains other code, and that dunder init file contains code that knows how to import that code. And you can now do interesting and useful things with that code. So let's go back to our geometry project here and kind of re-architect this by adding a geometry folder right here, and then immediately going into the geometry folder inside of our geometry folder, and adding, not another folder, please. Yes, I don't want this folder. Instead, what I want here is a Python file. And that Python file will be my dunder init file. Okay, so now I have a dunder init, and I'm going to move my geometry file in here, in there. So now I have the following structure. It's also in the diagram in here. I have a top level folder, it's called geometry. And in that top level geometry file or folder, I have another folder called geometry. And inside of that, there is a file called init. And I'll make this a little bit more specific because maybe I'll do geometry of other kinds of things later on. And I'll rename this file to refer specifically just to circles. So I have a package, it's called geometry. Within geometry, I have a file called circle.py that contains functionality for working with circles. The dunder init file, like I said, in the kind of simplest case, it is just empty as I originally created it. But in a more sophisticated case, it knows how to import some things from things that are next to it. So from .circle, the dot here literally means right here in this folder, there's going to be a thing called circle. Import from that thing the following names: calculate area and calculate circumference, which are implemented, the functions that are implemented inside of that file. Now, restarting the kernel on my notebook here, this code, import geometry as geo, still works, I hope, but does something slightly different. Didn't find calculate area, which we'll deal with in just a second. Instead of looking for, because it couldn't find we're sitting up here in this directory. Because it couldn't find a file called geometry.py, it follows to the next thing, which is to look for a package called geometry. So it's looking for a folder that contains a dunder init file called geometry. And it found it right here, which is good. And it's running, in fact, what it's doing is it's running the dunder init file when it does that import. And then populates its namespace, it's the namespace within for example, within this geo variable, the namespace that's populated within that is whatever ran in dunder init. For example, if I ran here a equals 1, let me restart the kernel here and run that again. I believe there should be a geo.a, which is equal to 1. So whatever code you put in the dunder init file is going to be in the namespace that gets imported when you run that code. And geo.calculate area is now the function calculate area. That was in there. Yes, question.
So let's say you made a new project that you still want to use your geometry package that you just made.
Yep.
Would you copy the entire folder over? Would you send me to like a different folder where you have all of the packages that you can experience on?
Yeah, the question is, okay, I have it inside of this project called geometry. I have this geometry package. It's kind of locked inside of this package. How do I use it across different projects? And I'll get to that next. So let's start with the simpler mode here, right? I have a package, it's in there, I have this dunder init file, I can run code inside of the dunder init, and when I import that code in the dunder init gets run, and if I imported geometry as geo, that namespace is populated by whatever variables get initialized in here or imported in here from other places. Okay. Right, and this is really generative because you can add a lot more stuff inside of this geometry. You can add subfolders that you import from, you can add, and we will add lots of other elements of the project can go inside of the package. You can have sub-packages, sub-modules, so this can get almost arbitrarily complicated. Shouldn't get arbitrarily complicated, but it can. So now, okay, to answer your question, now that you have your code in a package, you'll want to install this code on the machine that you're working on in a way that it can be imported anywhere, right? And so the next thing that we need to understand about the import statement is that, like I said, it starts by looking for a file called geometry.py, then it looks for a package called geometry.py. And if it doesn't find geometry.py right there, where it is, a package called, it will go and it will look to something called the Python path. The Python path is a list of file system locations, and it'll go by order, and it'll look for a package called geometry.py in those locations. Well, let's see what that looks like. There is, in the Python standard library, there is a module called sys, and that has a variable called sys.path, and that tells you what the Python path is. So you can see we have home Jovian geometry at the top here. So it'll look right there first for the package, and then it'll look at various other places. And on every machine, this will look slightly different. Here it's looking inside of a top level folder called SRV, and inside of that, it'll look into something called Conda. There are environments in there. There's an environment called Notebook. Inside of that, there's a library. And it looks first into this 310, then into libdinload, and then into site packages. In site packages, this kind of file system location called that ends with site packages is a pretty common one too, where things often get installed. We'll see later where things get installed when we use the tools to install things. But so if we end up putting our geometry package somewhere in one of these locations, or even creating a symbolic link from one of these locations to our current location, when Python runs import geometry, it could find it. If it's not right there, it could find it in one of these locations. If we put it in any other location on our machine, it will not be found and we can't import it. So how do we achieve that? Right. That's the next thing to do. one thing you could do, but would not be necessarily a great idea, is to look at your syspath and say, oh, okay, I see site packages right there. That's a great place to create a symlink, or let me copy all my code in there and put it there. And that's not necessarily a great idea, because what will often happen is a big mess at some point. You'll inevitably not keep track of all the things that you've copied into these various locations. These are ordered according to particular order. And what you want is you want Python in an orderly fashion to keep track of the things that are in these system path folders, and be able to install new things in there, keep track of what else is in there in order to make sure that the dependencies of different projects match. And so you want to use the standard Python mechanisms to install things, and particularly a library called setup tools, which will install things in an orderly fashion for you. So that's kind of the next thing that we'll do here. So moving on to. Okay. So I mentioned setup tools. Setup tools is a library, part of the standard library in Python, that is all about setting up code to be able to import, to be able to also install on other machines and so on. We'll see all the details of that. The main mechanism that setup tools uses is a file called setup.py. It can be called anything, I think, but by strong convention, it is called setup.py. And so we'll create that right there where we had our library. And we put it usually right above where our package is. So we put it right here where right now we have a notebook. We'll create a Python file and we name it setup.py. And in that setup.py file, I'll copy all this code from here. And put it inside of the setup.py, and we'll look at this in some detail. So the setup.py function contains an import from setup tools of two functions. One is called find packages, the other is called setup. Setup is really the workhorse of this library. It's a function that knows how to take instructions and install them in the right place in your machine. And the things that you give this function, you can think of them as metadata about the code. And so these are things that describe the code. There's the name of the package or the library, geometry. There's a string of the version. I'll come back to the version in just a second. The author email, where to find you, a description. You can have a short description of one sentence, but also a longer description. You'll see here that I'm reading it from somewhere that doesn't yet exist, which is a README file, but we'll come back to the README file in just a second. You might have a URL. This is really important. This line here calls a function called find packages. Find packages looks in the present working directory. Wherever you're running the setup.py file, it looks in the present working directory for packages, things that are folders that contained under in it, files, and it knows how to kind of describe to, or it actually, it runs and it literally passes those file system locations to the setup file as packages. This list of classifiers is a standard list of classifiers. We'll see where this plays a role, but this, you can think of this as, again, as sort of metadata about the code. Like, for example, which programming language this is written in, which license you'd like to apply, and we'll come back to the license too in just a second. If it's operating system specific, whether that's it, and then who the intended audience and what the topic is. For us, science research and scientific engineering is usually kind of like the intended audience and topic. And so if there's a catalog of software libraries and it knows how to organize those libraries, this is a good way to organize it, sort of like adding tags to, or adding keywords to an article so that some search engine or catalog can catalog your code to the right place. we'll see what the catalog is in just a second. And then you can write what version of Python is required. 3.6 is pretty old, so I'm going to go up to 3.8 here and require 3.8 at least. And then that just means if you're trying to install this on a system that's running less than 3.8, it will complain and say, I can't do that. And then finally here, there's libraries that may be required in order to run this code or even install this code. In this case, I've added one, which is NumPy. I could add more here, like, I don't know, pandas maybe. Oop. This is nice because it allows you to specify your requirements in a very specific form. You can even say, I need NumPy equal, let's say, let's see what the most recent version of NumPy is. I can go to the Python package index and look up NumPy and see, oh, it's 125.2. So let's say that I require NumPy version 125.2. So this is called pinning the version of dependency. Yes, question mark.
Yeah, is there a way to automatically populate this? Like just taking
Yeah. Yeah, there is a way to do that. Yeah, I think that speaks. So the question was if there's a way to automatically generate this list of dependencies, right? And that's because usually what happens is, for me at least, I'm working on some code. I'll say I've done sort of, I've been pretty meticulous and I've separated it in virtual environment where I'm working that's isolated from other environments. I'm working there and I'm like, oh, I need pandas. Let me install pandas into this thing. Oh, I need this other library. Let me install it in here. And I'm working on notebooks and I'm importing all these things. And I'm not really keeping track of like what are all the installation steps are that I'm doing. At some point, when I go to the library, I want this library to encode all these dependencies. And so I'll show the pip, which is the Python package manager in just a second. Pip can generate for you a list of the dependencies that are installed into your environment. I'll show that real quick here in the terminal. We'll come back to the terminal in a second to, so oops, yes. Pip freeze shows you what all are the things that are installed in here. It's showing it in a really annoying format though. There's probably a better way to do this because it's showing me all these hard code file paths. Well, let's figure it out later. But there are ways to generate a list of all the stuff. Here it's doing it in an annoying way, honestly, because of all these. It's telling me, yeah, I have PyOpenSSL, this library, and it's inside of this location, and that won't transfer very well to other people's machines. So you really don't want this list. You want a list that has things that look like this. PIMS 0.3.23. That will transfer. Yes, question.
Have you seen anyone use like a Conda like environment YML file to like feed into the function?
Right. So let me. So the question here is whether environment files for Conda can also be used in order to specify the dependencies in a setup.py file. So first, maybe I'll say a word about Conda for those not familiar with Conda. Conda, I've waltzed around it a little bit, so I'll say it explicitly. Conda is a system that allows you, an application that allows you to isolate different environments and create different environments on your machine. We saw a little bit of that when we looked at the sys.path here. It's actually, whenever we're working in a notebook here in the Jupyter Hub, we are working in an isolated environment called notebook that's isolated from other parts of the machine. We can create more of these using Conda. And one way to create these is by writing a file using the YAML format. YAML, the extensions is either YAML or .yml. There's a standard format for Conda that specifies environments. You can name the environment in there and you can say, I want the following libraries. It looks very much like the dependencies here. I want this library with this version and so on. Unfortunately, those two kind of formats are not strictly interoperable. You could potentially write some code up here that opens that file and processes the text in there and then creates this, this list. It's possible to do. but they're intended for slightly different purposes. So I wouldn't necessarily follow that path. Instead, I do what you're doing, which is installing my environment from that file, and then I kind of take all the dependencies that they're defined there and put them in the setup.py file, and inside of this install requires. There are other ways to do this. It gets quite complicated. There are other, I'm trying to show a relatively simple configuration here. There are other ways to specify these dependencies that get a lot more complicated. One thing that I did along the way here when I tried to do this was to open a file called readme.md. That file doesn't yet exist in here, and that's where my long description will go. So let me make that file in here. Maybe if I do a new file here, it will give me readme.md. At this point, when you're creating a library that other people might use, you might use in the future, it's not a bad idea to. It's in fact a very good idea to put a file called readme.md at the top level, and then describe what this thing is. Whoop. Once you're at this point and you're just about ready to release this to others, it's again a good idea to think about what you want other people to do with your code. If you're putting this code online, say on GitHub, and releasing it to the world, you might think, well, I've given it to the world and now the world can do whatever they want with that. But in most jurisdictions, at least in the US, in fact, you haven't. You still own the copyright to this piece of material. You've released it to the world so others can look at it. But when they look at it, they might be in a conundrum where they don't know what they're allowed to do with this thing. Are they allowed to use this? In what way are they allowed to use this? Are they allowed to sue you if something goes wrong? Are they allowed to use your name in order to advertise the product that uses this code? There are all kinds of legal considerations that are probably way outside of what you're interested in when you're releasing this code. And so one way to deal with all that is to put a license on your code that tells other people what they're allowed to do and what they're not allowed to do with your code. I assume nobody in the room is a lawyer. I might be wrong. I am not a lawyer, so I let lawyers take care of lawyerly things, in particular the open source initiative there it is, the steward of open source, and defines, it's an organization, nonprofit organization that came together, I think mid-20aughts, in order to kind of address the tensions that existed between people in industry that are creating open source software, people in academia, and so on. And one of the things that they define very nicely is a set of licenses that are approved by this open source initiative, that have been looked over by lawyers for you, and that you can choose from. There are many, many of them, a dizzying number, in fact, that are all compliant with their definition of open source. So all of these are open source licenses. It's pretty common, at least in the Python, neuroimaging Python community, to use one of the simpler, shorter licenses called, now I'm struggling to find it, but we'll work on that, BSD. Give me all the BSDs. The 2-clause or 3-clause BSD license. So you can copy this thing here, which is the legal document that we're interested in. Note the all caps. I'm not sure if that's the all caps is a legal requirement or what, but it is. And you can put your copyright on that. You can say, this is mine, by putting your copyright and name in there. And then it just says very simply what people are allowed to do. You're allowed to redistribute and use this with or without modification, provided that you're keeping my copyright when you redistribute it. You say, this is the code that I got from Ariel. Whether this is in source code or in binary format, and must have these conditions as well. So this entire license needs to appear there. And you're not allowed to use my name to endorse or promote products. And in all caps, don't sue me if something goes wrong. I think that's what this means, but again, I'm not a lawyer. So that's simple and straightforward, and I recommend doing that if you're going to release code to the world. And you can look at those other, if you have other considerations for how you want to share code, Some people in our ecosystem also like the much longer and more complicated, where is it? Clear search, the oft-used Apache 2. No, come on. It's got to be Apache in here. There, the Apache license version 2, which is slightly longer and has other kind of considerations too. So that also explains, since I put the license here in the README, that also explains to you the little detail here about what license. So here I wrote MIT, which is another relatively simple license, BSD license instead. So that's the license I'm using. And then I can add more description here of like modules in this library. Okay. Now, once I have that in place, I'm ready to install this thing. Let me just make sure that I am actually ready. Detailed all these things. Okay, we'll come back to Git and GitHub in just a second, but let me just show you how this is used first. So now my project that started out as a project with lots of notebooks has evolved, into something a little bit more complicated that contains a package, a README file, and the setup.py file that are the infrastructure for installing this code. So now I'm ready to tell Python to install this code such that it can be used in other places on the same machine. And the way that I will do that is by calling python-m pip install dot dash e dot. Sorry, that's a lot of things, but I think that's what I need to do here. Well, let's check that works. Looking good. Okay, I'll explain all of that I did. It's having some issues with me, but I'll tell you what happened. Okay, this tells it, use this module. So python-m name of module is a way to say, you have somewhere in your installation, I believe you have a module called pip. And that module, it's a library, but it's also an application. It's a command line application that you can run. Please, Python, find this application wherever you installed it and run it for me. Pip is the Python package manager. And in many places, you'll also see it called directly, pip install -e dot like that, or pip install some name of a package, name of library, right? Like that. You might have seen that in various places. That's an okay way to call it, but this one's really safe. And the reason it's really safe is sometimes Python has more than one installation of pip. And this one makes sure that the same installation that is installed under your Python interpreter, the one that you call when you call Python right here, is the one that's going to be used. So that makes sure that the software library that you're installing right now is getting installed together with the Python interpreter that you are using when you call Python. The rest of this install is a sub-argument of pip. -e is a special kind of case of installation. We're installing things in an editable format. And dot says, look inside this folder and install the thing that you find right here. So if you find a setup.py file, run that setup.py file for me and install things in the right way. So you see what happened here when I called this up here. It says, oh, I am obtaining the file that's right there. I'm preparing the metadata from setup.py. I'm going to have to collect NumPy of the particular version that you asked me for right here and install that. So I'm obtaining that dependency, and everything that follows down here are dealing with the requirements and dependencies. And then I'm going, because I had another version of NumPy previously, 1.24.4, I'm going to attempt to uninstall that, successfully uninstall that, and then I'm running setup.py develop for geometry. So it's installing that, and then in the end, it's telling me that it's successfully installed geometry version 0.0.1, because that is what's written in here, 0.0.1, and we'll come back to the version in just a second. So install that successfully, and it's also successfully installed along the way, NumPy 1.25.2. And so now if I take my notebook from here and I move it out of here, see if, yeah, I'll cut it from here and I'll put it somewhere else. I'll put it in a new directory down here, just to make sure my project in here. And I put this notebook, paste it in there, and restart the kernel here to make sure that it's not seeing what it previously saw. I can still run import geometry as geo. And now, one way to know where this went is to look and say, where is it? Well, it's looking right in the place where you put it, which is in your home Jovian geometry. Okay, let me pause here and then I'll come back to this -e story. What questions do you have so far? Yes.
I had a question about the, that you mentioned that it can have different versions. Is that because of like Python 2, Python 3 differences, or can you tell me about?
Okay, the question is, I talked a little bit about version issues here, like here it had to uninstall one thing and had to reinstall thing. Is this version issue, is this version stuff related to Python 2 versus Python 3? And the answer is no. As far as I know, this machine doesn't even have Python 2, and no one in this room needs to worry about Python 2 anymore, ever again, fortunately. This is more about the specific versions of specific dependencies like NumPy, right? So here's the story. All these libraries that we're using, pandas and NumPy, and you'll see others, they're all evolving and developing. They figure out that they had a bug in some functionality, they implement some new functionality, and they constantly release new versions of the software. They improve the way that the software works. And if you're using a particular version of that library that, for example, has a new functionality and you'd like that new functionality in your library, now you need to go to this newer version. Now, the way that the hub was configured originally had this version 1.24.4 of NumPy. But I said, hey, in my setup file, I said, hey, I want 1.25.2. I want the newest version of NumPy. Maybe I'm using some completely new functionality that just doesn't exist in 1.24.2. And that's what happened there. That little dance around here where it said, oh, I need to collect NumPy 1.25.2 was Python, the Python installation or the Python package manager saying, oh, I need to match the following dependencies for the following libraries. And here it's downloading. You can see it's downloading from somewhere. This progress bar here is the indicator that the Python package manager is downloading a new version of NumPy and installing it into my hub. Does that answer your question?
I was referring more to the bits that you were mentioning about using pip.
Oh, yes.
Like why is that?
This is just to be really, really safe. It is the case that if you have a laptop and you're installing Conda, for example, or Anaconda, that you will have a new Python interpreter sitting on your machine that was not there before. If you, like me, have an Apple laptop, Apple ships the laptop with a Python interpreter in it. It's in some place in your machine, and when you just bought it and you open a terminal window and type Python, it will use that Python interpreter. Now you go and install Conda or Anaconda, you'll install another Python interpreter in a different place. And when you type Python on the command line, you want to be sure that you're using that one. Or when you type pip, you want to be sure that using not the pip that came with your machine, but the pip that came together with Anaconda. So this is a good way to make sure that you're using the particular Python. So it's not a Python 2 versus 3, unless your machine is really old and has Python 2 installed in it. It's more about the fact that you can have multiple Python interpreters living side by side on the same machine. Yeah.
So you just change the path in order to know if it's going to be this. You have to specify it first in case you want to change that.
Yeah, so I could have called pip install -e dot like this, and it would probably be fine, but I'm not sure that it would be fine, because if I have pip, if I have multiple interpreters and multiple versions of pip, then, you know, I might want to make sure by calling which pip, which tells me which one of the different pips. In this case, if I just said, if I had called pip install like this, it would have gone to this one that's in notebooks bin pip, and that happens to also be right there together with which Python. They're in the same place. So these are matching, happen to be matching. But, you know, on different machines, you'll see different things where which Python and which pip end up in completely different places. That's when you need to worry. And it's a good idea to run python-n pip, because then you know that you're using the pip that is installed together with that Python interpreter. Okay, now this -e flag. -e flag is not how you would install any software. It's the way that you would install software that you are actively working on developing. That -e stands for editable. And you also see it, sometimes you'll see it, sometimes people install things in a develop with setup.py develop. So this is code that I am developing. And the reason that I want to install it in this particular way is that instead of, usually when you install software with pip install, you know, name of the package, it will download that package, it will put it inside of, say, your site packages directory or some directory in that Python path, and it'll copy that code and it'll put it there, put the entire module in there. What it does in this case is actually, it will not do that. Instead, it will create a symlink, a symbolic link inside of one of those directories, pointing to your home directory, to where your source code is, in this case, to this location. So it keeps, when you update the code, when we go and edit circle.py, it will change and import this again, restart the kernel in our notebook and import again, we will get the new version of the code without having to reinstall it every time that we make changes to the code, because it's not copying the code in a particular state. Instead, it's creating a symlink so that every time you change the code that Python imports is also changing. And I think that said everything except for one thing. Well, let me pause here. What more questions do people have at this point? Yes.
Just to make sure, so the command with -e is the same as if you type Python setup.py develop?
Yes, pretty much. Yeah. With some slight subtleties. Using pip also does a series of other things to sort of keep track of what versions of different things are installed on your machines. Okay, and you saw along the way it had some, you know, some incompatibilities, and somehow it dealt with that. It's saying, I have some issues. So I'm not exactly sure how that ended up resolving, but I see that it successfully installed things and I could import it. So I'm pretty happy. Let me just say one more thing about this version. Again, this version follows a very particular format. If you're creating software and you're thinking, oh, I might evolve this software over time, I might first develop a kind of initial prototype, and then I'll create more versions of this code. And you think that other people will use it and install it together with other things in the way that we're installing NumPy together with our code, you might want to tell other people about changes that you're doing via changes to a version stream and releasing incremental changes through incremental changes to the version. Thus, there are different conventions for writing these strings that describe the versions, and I'm following here something called semantic versioning, or semver, and you can read about semver on semver.org. There it is, semantic versioning. Nicely enough, this is a document that also has a version associated with me. It's a little bit self-referential, but there you have it. This is a semantic versioning version 2.0.0. And, you know, it has its ins and outs, like how you describe this and why you do that. Let's not go over all the details here. Instead, I'll just tell you that it's a way to communicate with users of your software and with other pieces of software about changes that are happening to the software. And if you're changing stuff that's we call this like the major version, the minor version, this here is the micro version. So I have 0.0.1, this is micro version number 1. That's telling people who use this This stuff is very early on in its development and it might change later on. We're not making any promises here. We're not even, but if you release a 1.0.0, now you're saying this is a major version of this thing. For the next, couple of cycles at least, the API, the application programming interface that you see here, will stay pretty stable. We're not going to break it too much. We've settled on this. We've discussed it. So this is a way to communicate to users about maturity of the software and about major changes. When I change this from 1.0.0 to 2.0.0, I'm telling you, okay, I've made some pretty major changes here. Maybe I broke some of the APIs that work with 1.0. Be careful when you're upgrading to 2.0. So that's just a way to communicate. And you can read a lot more about that in that Semver document. Okay, what questions do you have at this point? Okay, good. So, so here we have our project. And one of the next things that we'd like to do when we're building a project like that is to make sure that it works. Let me go to my notes here. And one way to make sure that things work is software testing. So we'll talk, I think for most of the rest here, we'll talk about various ways to test your code automatically. This is really important. I think Russ talked about that in his talk yesterday, and now I just want to show you the details of how to get started with testing. So one cool way of testing that we'll start with, Russ showed in his talk, he showed a little bit like write some code. The way to test code in an automatic fashion is to write some code that runs your code and checks that when you run your code, it does what you expect it to do. And one cool way to do that, that's also useful in terms of documentation, is to write something called doc tests. So here is, again, the doc string, and I've expanded it a little bit to include an examples section. Let me copy this examples section into our circle.py here. Okay, so you can write examples. The NumPy doc string specifies that you are allowed to call a section of your documentation examples, followed by, again, a series of dashes here just to say that this is a section. And then this herringbone here is a Python prompt. This is the prompt that you would get if you wrote the command line here. If you wrote Python, you'd get this same herringbone, 3 larger than symbols, or smaller than 3 symbols pointing that way. And so that's what you write here is you write this prompt. And then you can say, I want to run calculate area with input as 1. And when you run that in this example, you'll get this result. And that's the result that we can, in this case, calculate separately. We can run this code, for example. I can go somewhere else and run Python there and do import from geometry import calculate area, and then run calculate area with the input being 1. This has the benefit that this is the kind of thing that I could calculate with paper and pencil, right? The answer here is pi, up to some digits of precision. And when I look at that and I can say, yes, this is probably true. I know for this particular case of an input of 1, I know what the answer is. It should be pi, and it is pi. Seems like my code is working for this case. And so this example is a good example to put in my code because it's kind of the kind of thing that I could calculate with paper and pencil. Okay, and then so to run this, so now I've put it in my code and it's there as an example. If I produce other documentation, when somebody imports this in a notebook, they will see this example as part of the doc string. There it is. So that's an example for users. But also at the same time, I can run some code that will run this code, that will look for these examples embedded in my library code and run those examples for me. And that's done. I'll just make sure. Oh, PyTest is not installed in here. So I'm going to install PyTest, and we'll make sure that PyTest is installed later. Sorry, I should have tested that before, but there you go. So I'm installing, I've checked that Python and pip are in the same place. So now I'm installing a library called PyTest into my little corner of the hub using pip install in order to make sure that we all get that. I'll later change the hub configurations so that it's there, but bear with me. PyTest is a library, a Python library, and also a Python application called a test harness. Test harnesses are little applications that you can run in the command line, or little programs that you can write, or libraries that you can write Python code with that run your tests. They know how to find tests inside of code libraries and run those tests, and how to keep track of tests that are passing and tests that are failing. So now if I write, let me remind myself how to do this. Oh yeah, there we go. If I call PyTest with -- doc test modules geometry, I'm telling it, please run PyTest here. Find all the tests you can find here. I'm in the wrong place, but so this won't work, but oh no, it did work. Ideally, I'd run it actually inside of geometry. Run inside of here, find all the tests you can find in the doc tests, in the documentation examples, and then tell me A, how many tests you found, and B, whether they passed. And you can see PyTest obliged, it went, it found one item, which was this one test that I'd written. It ran that. That's this dot here says I ran this, and then one thing passed because the test is correct. Well, let me demonstrate what happens if the test is incorrect. Let's say that instead of putting the right answer, I put 1 in here, which is an incorrect answer. PyTest would then go and it would run that, and it would say, I expected to get a 1, right? The expected is really the thing that's written here, is what I expect to get. I wrote into my code what I expect to get. But what I got really was this pi, which is the correct answer. And so this doc test failed. You have one failure. It's showing me where in the code that happened. And it's keeping record of it's keeping track of that, all along. So I can run this once, I can run this twice, I can see that it doesn't work again. I can go, I can fix my code, and then I can run that again and see that it runs as expected. So this is one sort of neat way of writing tests. Actually, let me pause here and see what questions you have so far about test harness and doc tests and software testing more generally. Yes. Right. So the question is, how many tests should I write? How complicated should they be? What's sort of the best practice? It is best practice to write as many tests as you can within reason. There's no like hard and fast rule here, but it's not a bad idea to cover several different use cases. I'll show other examples of how you sort of harden this code to test other cases. So you can imagine situations where this would, for example, one thing that Russ talked about yesterday is making sure that your inputs make sense. So for example, you might let me go to other tests. I'll show later how you make this code, for example, fail when you provide negative radiuses, which are nonsensical, right? So we want to make sure that we want to test that when you give it a nonsensical input, it fails in just the right way. So we'll talk about that in a second. So you want to test, but to answer your question more directly is, you want to test corner cases. One thing that I end up often doing is discovering all kinds of bugs in my code. One way to make sure that the bug doesn't come back is that when you fix the bug, you put a test in that tests specifically for that bug. So it's also an iterative process. You it's a really nice, so Russ talked about test-driven development. Test-driven development is pretty hard for scientific software. You don't start out thinking like, oh, I'm going to do the following analysis and the result should be like this. That's really hard to do. Instead, what often happens is you write some code and you find some cases and you look at that. But when you find a bug, you can start doing test-driven development in the sense that the first thing you do is you write a test that should fail specifically for that bug. It looks for that particular bug that you found and it fails when that bug is present. And then you go and fix the code until that test passes. And now you know that that bug is for that particular case has been fixed. It can get really complicated because some of the code that we write deals with lots of data. There are like our data is noisy, so you don't necessarily see an exact result. It could be a result of some simulation. So I'd start with the simple cases first and go to the more complicated cases later. There's also the case that some of our code takes a long time to run, and you want these tests to run really quickly. The reason you want them to run really quickly is that if they start being really slow, you'll stop running them. And tests that nobody runs are not useful. So you want to make sure that the tests are these like atomic little things that run really, really quickly. If you have hundreds of tests, you want that thing to run in a minute or two, not in 4 hours. We do end up often with test cases that take a long time to run. What we do is we separate them out into kind of a separate run, and we run that overnight. So we have something set up to download the software and run it every night so that the complicated long cases still get tested on a daily basis, at least. So we know that when we've broken the code, we at least know. Okay. So this is one mode of testing, docstring testing. Another mode of testing is by writing a test suite. So inside of my package here, I can create a folder called tests. And inside the folder called tests, I will create a file, a Python file called test circle. Notice this library is relatively simple. It's kind of a one module library. It's got this one package library. It's got this one package called geometry. Inside there's this module called circle. If I added another module called square, I would create a separate test file in here called test square. And this all follows, again, as you might imagine, a pretty clear convention. The test harnesses like PyTest that we're using here look for folders called tests, and inside that it looks for files called test underscore something, and inside of these it will look for functions called test underscore, for example, what was the name of the function? Calculator. So looking for this function, and then it will run this. It will run this function when it runs the test suite. When we call PyTest on this library, it will run this file, and it will run the functions called test underscore something. So from geometry, import calculate area, and then what I'm going to do is I'm going to run calculate area with a known input, and this is result equals, and then what was the result supposed to be? It's supposed to be pi to this precision. Okay, I'll explain all this code. So I've written a little bit of code here. The way this code is constructed is a series of calculations and a series of assertions. So this line here is the important line, is the assert statement in Python. This statement right here is a keyword in the language. And what it does is that it takes two inputs. The first input here is some piece of code that has a Boolean value associated with it. It's either true or it's false. And then it takes some string over here. if this line of code, if this input into the assertion, into the assert statement evaluates to true, nothing happens. It just keeps going. However, if this is false, this will raise an assertion error, and it will also give you this message. It will also send this message to the user. So let's evaluate that. Now I'm going to run PyTest without the doctest modules. And now what it's telling me, I found this test inside of test circle. I ran this one test and it passed. Again, let's, for the sake of demonstrating this, let's change this to 1 and see what happens then. In that case, it runs this and it tells me that an error was raised. Any error that would be raised from this code would bubble up here and show up in this output. In this case, it's saying there was an assertion that this number is equal to that number. That's wrong. And the assertion area of radius 1 is not pi. And that's the message that I had planted in here. So it's a good idea to put interesting messages in here. Now I've fixed that, and now when I fix that, it works as expected. Okay, what questions do people have about that? Okay, so I think, let me try to, yes, question.
You ever have to consider what information you're using? Like if it's run on Mac or something versus others, and whether you're doing specific with that?
Yeah, the question is, do we have to take into consideration different operating systems and how they behave? And the answer is usually not. If you're lucky, no. But if you're unlucky and you're doing something that interacts with differences between these operating systems, you can test for that. You can say, if I'm on this operating system, do the following thing. If I'm on that operating system, do this other thing instead. And if you're lucky, you'll never have to do that. But if you are unlucky and you're doing that, then Python knows what operating system it's running on. You can do, I think it's os.platform, gives you back a string, but it's just different for this different platform. Okay, what other questions do people have so far?
The questions in chat.
Oh, there's a question in Slack. Oh, there's a lot of things going on. Okay, what about if I have a mother class and root folder with the package name? Okay, so the first question here is about, goes back a little bit, is about object orientation and how this interacts with the package structure. I'll say the following: many packages have, in many cases, I've done this a lot. You have some kind of, well, I'll give a concrete example. In the DiPy library, which deals with diffusion imaging in Python that I work on, we have many models for diffusion. And all those models share some common properties. For example, they all need to know about the acquisition, how the acquisition is done, what the directions of measurement were, what the b-values were. So all those models need that information. And so it made sense for us to create a base, what we call base class, that stores that information as part of the object. But then there's a host of different methods over here, like DTI and DSI and DKI and lots of other acronyms to do with diffusion MRI. And each one of those inherits from that base class and then implements its own thing. Because those things are quite different from each other in terms of what they do, it made sense to put each one in a separate module with all of its kind of associated functionality. And in that case, it made sense to put the base classes in one place, in one module that implements the base class, tests the base class, where we can put all the things that go into all the models and we can test for those. So in that kind of case, it makes sense to have sort of a module that has the base classes and then other modules that import from that, the base class, and then implement other classes. I hope that answered the question about object orientation. What about if you specify an older version in your measurement? So this is about the version mismatches. So the answer to that question, which is like, will pip fix everything for me, is sometimes yes and sometimes no. And sometimes it gets really complicated because you have one set of dependencies for one of your dependencies has one set of dependencies, another one of your dependencies has another set of dependencies. Those change with the versions that those dependencies use. And you can end up in a situation where pip tells you, well, this library asks for NumPy 1.24 and this library asks for NumPy 1.21, and there's no way that I can do both of those things at the same time. Figure it out for me. Tell me what to do here. And then you need to sort of figure it out, which versions of those other things match so that you can get the same version of NumPy. So it won't always fix it for you, but it'll tell you, it'll point in the right direction. Then the other question is, when should we use PyTest, unit test, or other testing libraries? Are there any preferences regarding choosing test libraries for analysis scripts? I tend to depend pretty heavily on PyTest. It's pretty nice because it allows me, I can use it as a library also to write other code that does things around my tests. Unit test that I believe the sort of Python built-in test harness. So there's no intrinsic preference for one or the other, except that I use PyTest a lot. Just I guess I'm used to it. And the overall kind of scientific computing ecosystem tends to use PyTest. So a lot of people use it. There are a lot of tools out there for doing things related to numerical computing that use that. Okay. So let me go back here and just maybe try in the remaining time to show you a little bit about how you combine what we call defensive programming with testing in order to build more robust functionality. So we kind of referred to this by saying that R cannot be negative for this function. So if I get an R that is smaller than 0, I should raise an error. I should say, I'm going to raise a value error here, but there are other errors you could raise. And that value error should say something like radius inputs should be non-negative. So for negative numbers provided, this should fail. It should raise an error. And I want to test that actually happens. So for that, I'm going to have to look up how PyTest does this because I never remember. Search raises. Yeah, there we go. With PyTest raises. So this is where PyTest, and I don't want a 0 division here. I want a value error. So what I'm telling PyTest here is, and I need to import PyTest here. I'm saying when you run the following code, calculate area with -2, within this context, you should be raising a value error. If the value error was not raised, that in itself is a problem. Let's do this test driven instead of like I did now. So let me remove this piece of code here or comment it out. I'm commenting this out. Right now, the code is not defensive, and the test fails, and that is because the code did not raise an error as expected. My testing code expects there to be a value error, but there isn't one, and because of that, the test fails. Now, if I put back my implementation of this more robust testing, then now it's running the test and it's coming back green. So it did that. I can be a little bit more explicit to. I'll just add a detail here to make the whole thing a little bit more explicit for you, and also. This is not a bad idea to make each test a separate function. It also feels more satisfying because now, it didn't actually run that because I didn't save it. Right, now you get 2 dots here. And if you work on this for months and years and you add hundreds of tests, you'll get like a whole wall of dots in there. That's really satisfying. So, granular testing. I'll just add a little bit in case, for those of you who are not familiar with this Python construct, is that a statement, this keyword with defines what's called in Python a context manager. It's another kind of more advanced Python construct that is not often used in sort of analysis code. And the idea is that within this context, within the indented code under here is defined as a context. And in this case, this context lives with this idea that within this indented block of code, a value error should be raised, otherwise PyTest will keep track of it. So it's a little context within this. You can do other things with context managers, like often context managers are used in order to open files and make sure that that file is closed at the end of the context. There are various things that this is used for. In this case, it's a very specific kind of context that has this condition on it that PyTest should raise an error. So that's how we combine defensive programming. This piece here is our defensive programming that will raise an error when the inputs are negative, which shouldn't make sense in this code, together with testing for that particular condition and the raising of that particular error. And so as you evolve your code, you'll add more and more tests for more and more different conditions. You'll produce bugs and you'll fix your code to do that. For example, as an exercise for the reader, because we're almost out of time, this code here should not work. There's a very particular use case that I talked about much earlier, where this is just going to fail miserably. I just didn't write this code to take into account a very common use case. So the use case that I actually have in my notebook is not covered by this code. So this will fail, and I'll have to fix this pretty quickly if I start using it. Any guesses? Yeah.
It is 0.
0 radius is fine, right? This is an object that has no radius. Maybe 0. Yeah. Other guesses as to what I failed to take into account here? I'll provide the answer then. This won't work if R is an array of inputs. I don't think that, so it will test against 0 and it'll say this number is larger than 0, this number is smaller than 0, and so on. But an array of true and falses doesn't have a defined Boolean value. So I need to do something like np.all R smaller than 0 or something like that, or any, actually, in this case, if any of the, I think something like that might work, but it gets more complicated. So as I work out, I might run into these things and go and fix my code. Okay, I'll pause here and then see what other questions people have. Yes.
Let's have a general question. So when we're talking about DIPy and how you decided to construct the models, I feel very overwhelmed when trying to think about how to organize things. And
Yeah.
Best practices are like lots of ways that you approached it.
Yes, the question is, I described the structure where the base classes and then there are classes derived from that. And the question was, is there any sort of resource we could go to that would kind of describe this? And so I think the broad topic that we were talking about is like software architecture, software design, and there's oodles of books. One thing to look for is design patterns. There's a book, The Gang of Four Design Patterns book, contains descriptions of these kinds of patterns. Like you might have a pattern of, like a base class or with these derived classes. I'm actually blanking out on names of patterns right now, but there's one book called Design Patterns.
And what was it on?
Design patterns. So this broad topic is about design patterns. It's like software gets really, really complicated, and now you need to think about what is the design of my software. Software architecture is another broad. Yeah.
When you're using the concept, you mentioned DIPy or some other
Yeah, so the question is, when writing software for neuroimaging, what should we rely on? And there's a lot of nice software packages. You'll hear later this week also about some of these software packages. I believe Elizabeth Dupree will talk about NeLearn, which is a really good one to depend on. The software ecosystem for neuroimaging, you can describe it as this kind of layered thing. At the bottom, we have things like NumPy and SciPy, which implement sort of the core computational things. And then on top of that, people have built other things like one that we use, that everyone can use a lot is called NeuroBabble, which is for reading and writing neuroimaging file formats. That's sort of essential and at the heart of the neuroimaging Python ecosystem, because the data shows up in some format and you need to read it, you want to write it, and so on. And then on top of that, people have built various things for specific modalities or specific kind of applications, like DiPi for diffusion imaging, or like, say, fMRI prep for pre-processing fMRI. One that helps put together a lot of different things in NiPype, NIPYPE, which also interacts with non-Python software and allows you to build pipelines. So that's pretty handy as well. I'm probably forgetting something essential, but we can also take this to Slack, see what people are using, like folks in the. Let me just check with Slack and see if there are any more new questions here. I see none. Okay, so with that, I think I will wrap this up and we'll go for lunch break. We'll come back in 90 minutes for the next thing in the afternoon, which will be Git and GitHub. So this is two separate things, just a bit of guidance there, because you're probably asking yourself, where should I go? One will be sort of start with beginner level. If you don't use Git, say, or haven't used Git for anything ever, then go there and hear about the more sort of introductory level of using Git and GitHub for version control. And I will go really fast through that and try to get to the point where we're sort of collaborating on projects together by using GitHub. So I'll assume that people have used Git in some capacity. All right, cool. See you in 90 minutes.